Okay, students, welcome to video class 22. And in this video, we are again sticking on to stability analysis, as I told you earlier. But new topic is root locus. Okay, so you may not be familiar with this anyway. And since this may be having some more sessions, I'm calling this as root locus part 1. Okay. In the previous videos, we have studied about RH criterion, right? RH criterion, and using this, we analyze the stability of a control system by solving, that is, by using the characteristic equation of a of the of a closed loop system. Now, just for a recap, what do you mean by the characteristic equation? Equating, so if you have the transfer function as gs by 1 plus gs hs, and you equate this 1 plus gs hs to 0, that is your characteristic equation. Okay, so this is your characteristic equation. Solving this characteristic equation and see that whether the roots are on the left half or right half. Okay, whether the roots present in the right half of the left half, and if any one of the root lies on the right half, on this half, that is on this half, then that's it, system is said to be an unstable system. But in order to instead of solving directly this characteristic equation, we know how to find out the root array from the given characteristic equation, as well as root array, and finding out the root Hurwitz determinant, and later on applying the criterion on the first column of the root array, and thereby we have found out that by applying the criterion, we have seen that the number of roots on the right half is equal to the number of sign changes of the RH criterion. Well, this is another method, root locus, or rather this one can be called as a mathematical method, and which is an example of an absolute stability, which gives you only an answer to a question whether a system is stable or not. While this root locus is actually a graphical method. It's a graphical method, and it will give you more information than just an yes or no answer to the question whether a system is stable or not. Now, this RH criterion or RH method will give you only an yes or no answer whether the system is stable or not. But this graphical method will give more insight into the about the regarding the stability of the system. Okay, not only it will say that whether there is any whether it is stable or not, it will also gives us a provision to predict or to conclude certain things, and from a designer point of view, this method is more useful than the RH criterion. That's the first difference between the root locus and RH criterion. Both the methods are used for stability analysis. The first difference is this is a RH criterion is a mathematical method, while root locus, I will come to this later. What is this root locus? Root locus is a graphical method, so that it will be more informative than the RH criterion. Now the second difference is, now in the RH criterion we use the characteristic equation of a closed loop system, while in root locus we will be using open loop transfer function of a closed loop system, right? Closed loop system, right? Using the open loop transfer function of a closed loop system, we can again ascertain the stability of a system having the transfer function g of s by 1 plus gshs. What do you mean by open loop transfer function? Open loop transfer function is nothing but it is gshs, right? And we have also seen the seen the general expression for GSHS for an open loop transfer function as, I'm again rewriting, I have already shown you in the previous video. For details you may refer those videos. 1 plus STA plus into 1 plus STB, etc. It goes on like that, divided by s raised to n into 1 plus st1 into 1 plus st2, and it goes on like that. Now we have seen that this k is called as the path. K is called as the scale factor, or you can call this k as the forward path gain. This can be called as a forward path gain. Okay, now from now onwards we'll be calling this k as, it's not simply a scale factor, it can be called as a forward path gain. Okay, do remember that. While n refers to what we have already seen when we studied about the steady state error, this refers to the type of the system. So based on this value we can classify a system into type of system. Anyway, that is not the subject of this module. Okay, so we have an idea already about this open loop transfer function. This is given by this expression. So we cannot a particular constant or particular thing called as a forward path gain, which is of an immense importance in the analysis using root locus. Okay. Okay, so in the last session we have studied that using 1 plus GSHS equal to 0, okay, that is your characteristic equation. Using this characteristic equation you can ascertain the stability of the system. That is, you are to find out the roots of that equation, right? Now using this characteristic equation, one of the things that you need to do is the factorization. So now as we have seen earlier, that as the order increases the factorization becomes tedious, and not only that, when you substitute this, you can see that this 1 plus k into the whole this thing, 1 plus sta into 1 plus stb, okay, etc., up to s raised to n into 1 plus st1 into 1 plus st2 is equal to 0, right? So in this characteristic equation there is a term called as a k, and which I have already defined as the forward path gain. Okay, so now this forward path gain is a thing which a designer can design. Okay, it is the it is the it is the designer's responsibility to to select this k. That means even though k is a constant for a particular system, the k is a thing which is designed. So a system can be designed for various values of k. Now this transfer function, okay, this is the characteristic equation. Upon solving this characteristic equation you will be able to find out the roots, right? But we can see that if k varies also, because this is the characteristic equation, since k varies, the location of the roots can also vary, right? So this is a forward path gain, and the k is since gain is a positive quantity, gain can vary from 0 to infinity, right? So as k varies from 0 to infinity, this particular, as k varies, the solution to this characteristic equation will also vary. That means the root also varies. Okay, so you can, when you plot that in a s plane, it seems that as k varies, the root also varies, meaning the root location varies. Root location varies. Okay, as k varies from 0 to infinity, I will be explaining with some examples later, so you will understand the meaning of this root location variation, right? And when you uh, when you complete, or when you trace that path of the variation of that root location, that becomes a locus. What do you mean by a locus? Locus refers to a path, right? For example, if you have a if you have something called as cos theta plus j sine theta, okay, what is the locus of this function? If you have a function like this, you will say that this is a circle, because always as angle varies, right? Angle, here is the theta. Now theta varies. For every theta there will be a value for cos theta and j sin theta, and whenever you take the magnitude of this, that is magnitude of cos theta plus j sin theta, becomes equal to 1, right? So this traces a path. We can call this as a circular locus. So similarly, as k varies from 0 to infinity in an S-plane, this the open loop poles tends to move, right? And that path of that motion is what is called as a root locus. Okay, so you will understand by some examples. Okay, now from this you can say that 1 plus GSH is equal to 0, meaning that 1 plus GSHS is equal to 0. That is the characteristic equation. Now to all the roots of this equation, say call this as equation 1. Equation should satisfy two conditions. One is, say, what is this GSHS equal to? Then what is GSHS? GSHS equal to minus 1. Or when you take the magnitude of this magnitude is equal to 1. So this condition we call as the magnitude condition or the magnitude criterion, right? Magnitude criterion. And so you can come to another conclusion that any roots of 1, that is, when you solve this characteristic equation, any roots of this characteristic equation should satisfy this condition, right? The magnitude criterion. Similarly, you have another criterion called as a angle criterion, and the angle criterion is nothing but you have to take the angle of this. That is, if you have a plus jb, then the angle is tan inverse b by a. So if the angle of g of hs, the angle of g of s h of s has to be equal to 2k plus 1 into 180 degree, where k varies from 0, 1, 2, etc. So this must be the angle. So this is the angle criterion. Okay, so for a point to be on the root locus, that is our objective is to draw a root locus. Okay, the location of the poles as k varies. We have so far studied till the previous video, k is considered to be a variable, right? Sorry, k is considered to be constant. Now what we are going to see is we have framed out this general equation for a characteristic equation, and we have seen that this k can be varied by the designer. So as k varies, the root location also varies. So now we know that there is a scope of variation of k from 0 to infinity, which is the system gain. Now as the system gain varies, the roots of a particular characteristic equation also varies, and the path that particular root traces is what is called as a root locus. And as it moves, each and every point of that root locus has to satisfy two conditions. Condition 1 is called as a magnitude condition, which is angle GSHS equal to 1. Condition 2, which is called as the angle criterion or angle condition, that is angle GSHS has to be equal to 2k plus 1 into 180 degree. Okay, so these two conditions are very important, and whichever roots satisfy these two conditions will be the roots of 1 plus GSHS. Okay, now I'll be giving you some examples of to give you a feel of what root locus is. Okay, so as an example 1, this is not the problem of root locus. This I will be giving you 1 or 2 or 3 examples just to give you a concept of root locus. Okay, I mean, so far I've just explained in words that you may not be understanding what root locus is. Okay, this is not the actual root locus problem. This is simply a scenario where we consider a closed loop system. What is this? GSHS. GSHS is what is called as the open loop transfer function. This is the open loop transfer function of a closed loop system. Okay. Now you have been given k. It is been given as k is by s plus 1. Okay. Anyway, in the procedure of root locus, we are not going to find out the characteristic equation, but I'm just finding out the characteristic equation of this. Now, what is a characteristic equation? Once if you know the open loop transfer function, just add a 1 and equate to 0, and this is your characteristic equation. This one is your characteristic equation, right? Now, what I'm going to do is, I want to, so that you can write this as 1 plus ks by s plus 1 is equal to 0, right? Okay. Now from this, I am going to represent this s in terms of k. S in terms of k. That means I have already mentioned to you k, even though k is a constant, k is a parameter which can be designed by a designer. So a designer can design the value of k from 0 to infinity. So in that perspective, if k can be considered as a variable, then this characteristic equation can be thought as a function which not only varies according to the location of the roots, which also varies according to the value of the gain which is designed. Okay. Now, using this, you can take this k into s. Okay, take this, this will be s plus 1 plus ks divided by s plus 1 is equal to 0. Okay, so from this you can write this as s plus 1 plus k s is equal to 0, right? Or from this you can write this as taking this s as common. So s is 1 plus k is equal to this plus 1 is equal to 0, or s into 1 plus k is equal to minus 1. Okay, so now s is equal to, that is the roots. You're going to find out the root in terms of 1 plus minus 1 plus k. So what I told you earlier is, as k varies, the root location varies. Now you have the root of this characteristic equation of this open loop transfer function, right? Look at this open loop transfer function. Now the denominator suggests that that is a first order system anyway. So that means you only have a characteristic equation which is of having the order 1. That means it will be having only one root, and that root is given by s is equal to minus 1 by 1 plus k. Now we have seen that this k can vary from 0 to infinity, and for different values of k, this will be having different value, right? This s will be having different value, and that's what we are going to find out next. Okay, now this root, this is actually what? This is actually a root, right? Root of what? Root of this characteristic equation, right? Okay, now we want to know how this root varies according to the value of k. Okay, now what I'm going to do is, I have already told you that this k can be varied. So this characteristic equation is going to be, or this root location is going to be a function of k. Now I'm going to arbitrarily select some values of k, and I'm going to find out the various values of yes. Okay, here is the table for that. Okay, so here are the values of k which I have arbitrarily selected. That is, I have varied from 0 to infinity. So just put k is equal to 0. K is equal to 0 means this becomes minus 1, right? So this is minus 1. S is going to be minus 1. When you put k is equal to 1, this will be minus 0.5, right? This is minus 0.5, right? Then what about at s is equal to 9? When you put 9, this becomes minus 1 by 10, or this becomes minus 0.1. When you put 99, you will get this as minus 1 by 100, or this becomes minus 0.09. 0, 1, right? And what happens when you put k is equal to infinity? When k is equal to infinity, it is 1 by infinity, or this becomes 0, right? So what we have seen is, as k varies from 0 to infinity, the root location at k is equal to 0, the root location starts at s is equal to minus 1, right? Now, this s is equal to minus 1 is actually what? Actually, the pole of, what is this s is equal to minus 1? This is actually the pole of what? Of GSHS, right? Or we will call this as the open loop poles. Open loop poles of a closed loop system, which is actually s is equal to minus 1. Now what happens to that s is equal to minus 1? That pole location is moving, right? Is moving from minus 1 to a point where s becomes equal to 0 as infinity. Okay, when you try to plot this on an s plane, this is an s plane, this is a real and this one is the imaginary term. Even though this is a real plane, in this example there is no imaginary term, so all the points will lie on this real axis, right? Now let's plot at k is equal to 0, at k is equal to 0, right? At k equal to 0, k equal to 0, this pole starts from this minus 1, right? Now this is actually what? This is actually the open loop poles. Open loop pole, or the pole of an open loop transfer function, right? So the pole starts at k is equal to the root locus. Actually it starts at k is equal to 0, right? And what happens at k is equal to minus 1? Now this has reached, now as you can see, as k varies, this has reached here. So this is the point corresponding to k is equal to 1. This is minus 0.5, right? And the 0.1 will come around, right? Minus 0.1 will be k is equal to 9, and this will be k is equal to 99, and this is the point corresponding to k is equal to infinity. Now is there anything to change up beyond this? No, this is the maximum value of k. So what happens as k varies from 0 to infinity, we have seen that the open loop open loop pole of this particular system moves from 0 to s is equal to minus 1 to s is equal to 0. Okay, so in no way this root comes to this side. For every k which can be designed, uh, that will remain on the left half of the S plane. As long as the root lies on the left half, you can pretty sure that that system is a stable system. Now this will be reaching only at k is equal to infinity anyway. K is equal to infinity is a point which cannot be attained practically. So you can say that this particular system will, in any case, whatever may be the gain that you design, this will always remain on the left half of the S plane. So you can have the, you can say that, come to a conclusion that this particular system will not be an unstable system. Okay, and it will be a marginally stable system when k becomes infinity. So till that point, you can be pretty sure that the system in no way, whatever may be the value of k, that's not going to reach at the right half of the S plane. So look at this. This path, okay, this path, okay, this is the path that the root travels. Okay, this is the path that root travels. This is the path the root travels as k varies, right? Right? And this path is what is called as the root locus. Okay, now by looking at the root locus, we can predict the stability based on the value of k. So in some, we will be seeing some more examples regarding this to give you a feel of this root locus. So this root locus depends on the value of k. So the designer in this particular system, he can simply design for any gain, because he's pretty sure that his root locus is not going to cross this this imaginary axis and comes to this right half. So we know that whenever the root comes on the left half, that's going to be an unstable system. So we have seen, one point we have seen is a root locus always starts. This is root locus starts from the open loop poles, right? This particular system, actually we have started with the characteristic equation, and we have found out s in terms of 1 plus k, and I mean coincidentally it comes as k is equal to 0. We have seen that s is equal to minus 1. It is nothing but it is the open loop poles, and in the coming examples also we will be seeing the same thing, and later we will try to conclude certain things. Anyway, the two things that you need to that you have you must keep in mind is root locus. From the root locus you will get two ideas. One is you will have the you will be having the nature of the time response, right? The nature of time response, right? So as long as this is in the this is a the response will be now in this, as it moves in this, we have seen that this is also the case where there is no damping, over damped system. Okay. Now another thing is that you just need to study this only. Another thing is that it will also say something about the system stability. Okay. So system stability and the restriction that you can put for system stability, all you will understand in the later examples. Okay, now let's move on to example 2. So you are having a open loop transfer function which is given by k by s into s plus 4. So as usual, you can have the characteristic equation. So that is 1 plus gshs equal to 1 plus k by s into s plus 4. So I again repeat, for root locus, for our study of root locus, we require only open loop transfer function. I am using this characteristic equation just to give the feel of root locus. So this is 1 by 1 plus k by s into s plus 4, it is equal to 0, or you can take the LCM and this is equated to 0. Okay, manipulating this, you will get this as s into s plus 4 plus k divided by, taking the LCM, you will get that like this, right? Is equal to 0. From this you can come to another thing, s into s plus 4 plus k is equal to 0, or this will be s square plus 4s plus k is equal to 0. So this becomes a quadratic equation, meaning that this is actually your characteristic equation. So this characteristic equation suggests that this is a second order, this is a second order equation with two roots, right? So this there are two poles for this characteristic equation for this closed loop system. So this will be yes, S1 and S2, right? Right? Now you can find out this S1 and S2, these two roots, the roots of this characteristic equation, right? So here also in the first example also we plotted what, using this is actually the root of what, root of the characteristic equation. This is also the root of the characteristic equation, right? Now that is the basis of the stability. For a stable system, the roots of the characteristic equation should not be on the right half. Okay, but we have seen that what is actually the need of this root locus, because we have seen that this forward path gain has an effect on the roots of these characteristic equation. That's what we study and by root locus. Okay, now from this you can simply say, using minus b plus or minus root of b square minus 4ac, you can use that expression, and you can see that that will be minus 2. One of the root will be minus 2 into root of 4 minus k. You may do it by yourself. Find out s2 as minus 2 minus root of 4 minus k. Okay, now let us tabulate. So you have two roots. In this case you have only one root because that's only a first order equation. Now since it is a quadratic equation, so you will be having a through 3-row table, and here is it. Okay, now we have these two roots in terms of k. So as I told you, your k can vary from 0 to infinity, right? So now using that I have selected some k values 0, 2, 4 and 8. So substituting on these k's, you will be getting s1 to be, so when you substitute 0, both s1, so s1 is 0, right? When you substitute k is equal to 0, this is 2 plus 2 minus 2, which is 0. Now when you substitute k is equal to 0, here you will be having again this as 0, 4 minus 0, that is root, minus 2 minus 2, which is actually equal to minus 4, right? Now then again you can see that at k is equal to 2, s1 becomes minus 0.6 while s2 becomes minus 3.4. You may just do it by yourself by substituting the values. Just verify the answer is right or wrong. This is minus 2 and minus 2, and again you have minus 2 plus, when you put 8, this becomes minus 2 plus 2j and minus 2 minus 2j. And what happens at infinity? At infinity you can see that s1 becomes j infinity, right? So when k becomes infinity, this is when k is infinity, right, root of 4 minus k, so this is minus j infinity, right? And so this will be j infinity and this one will be minus j infinity, right? Okay, so this is plus infinity. So look at this, root of 4 minus infinity is infinity, so this is plus infinity, plus j infinity, right? Plus j infinity, while this one becomes minus j infinity. Okay, hope you understood this. That is, this is 4 minus infinity, so that means this is minus infinity, or you can call this as j infinity, right? And you have a plus j, right? So this is plus j, while in this case this is minus j infinity. Now let us try to draw this S-plane. Look at this. So you're going to plot these two, so for S1 and S2. Now look at this, for values of k is equal to 0, you have 2 points. Now in comparison to this root, you have only 1 point for a particular value of k. Now here, in this case, at k is equal to 0, you have S1, which is a pole at the location 0, and you have another pole at s is equal to minus 4. Now look at the beauty of this. What is the open loop poles? Now when you consider this open loop transfer function, the poles are s is equal to 0 and s is equal to, look at this, okay, s is equal to 0 and s is equal to minus 4. Now when k is equal to 0, this becomes, this is the point corresponding to both the roots for k is equal to 0. K is equal to 0. Okay, so now the root locus, now in this case there is only one source of the root locus. That means root locus starts only from one point, while in this case the root locus starts from two different points. That means you have two root locus. That is, one is the locus of the locus of pole s is equal to 0, another one is the locus of the root s is equal to minus 4. So your root locus starts from the open loop poles. That is, that will be always the value corresponding to k is equal to 0. Now let us see what happens at k is equal to 2. K is equal to 2, look at this, s1 moves in this way, right? Now s1 is so this is k is equal to 0. So this actually corresponds to s1, or this is the root of s2, right? This is at minus 4. Now as k varies, k is equal to 2, this becomes, this s1 moves in this direction, right? And it reaches at 0.6. When it reaches 0.6, we call this as k is equal to 2. Now here also it changes to minus 3.4, so it may come somewhere here, right, at k is equal to 2. Now At a particular k, that is k is equal to 4, we have seen that both the roots meet together at a point at minus 2. Both has having the same value. So these two roots moves. Okay, so this path that these roots traces is what is called as a root locus. Okay, now what happens at and if you go on increasing 8, what happens? At a particular value greater than 4, one root, that is S1, moves in this direction, minus 2 plus 2j. This is minus 2 plus 2j is in this direction. So among the one of that is this S1, this is your S1, right? So this S1 and S2 meets here. Now that is going to be a tussle. There's going to be a war between those two. They meet together, they don't like each other, they will have to part. They fight and part in such a way that one S1 moves in minus 2 plus 2j is in this direction. So one will be going in this way. This is minus 2 plus 2j, right? This is minus 2 plus 2j is a point here, right? So this will be like this, and this will be going in this way. So this is minus 2 minus 2j, right? Now you may just put any other values other than, values greater than 4. Let's say 9, 10, 11. Every time you can see that the real term is always going to be minus 2 in this case. So that means that's why I have drawn. You might be thinking, why can't I draw in this way, or why I have drawn in exactly perpendicular to each other? The reason is, for what all values greater than 4, the real term is going to be minus 2. That is, real term is fixed in this problem. So that means it is straight. It's not like this, it's straight, right? It has to be drawn straight from this point. From this point, it has to be straight like this. Okay. Now, this is actually the root locus. So you can say that this is the root locus of S1, while this one is a root locus, this one is the root locus of S2, right? So what do you say about this system? Will the system ever come to a point of instability? Never. Because as whatever may be the value, now at infinity, this is going to be plus j infinity. That is somewhere in the left half, right? So that is plus, this will be minus 2. This is minus 2 plus j infinity, and this is minus 2 minus j infinity. This is what you need to write. This is minus 2 plus j infinity. This is minus 2 minus j infinity. There also the real term becomes the same. The real term is the same. So in no way this root crosses this imaginary axis to come at the right half. That means you can again come to a conclusion regarding this system as a stable system. Okay, right? And this particular system will be having no oscillation till the value k is equal to 4, right? So as long as the root lies on the RH on the real axis, there will be no oscillation. Now as it moves towards the imaginary axis, then there can be oscillation. That is for sure, right? If you have an imaginary term, that is j omega, so if there is an omega, then there will be some oscillation, but that will be a damped oscillation because all the roots resides on the left half. Every time, for whatever may be the values, both this S1 and S2 lies on the left half of the S-plane, proving that this system is no longer going to be an unstable system for whatever values of k designed. Okay, hope things are clear. So from this, let us draw some conclusion. We will be listing all this again later. So one of the things which we have seen in these two examples, the root locus always starts from where? From the open loop poles, right? That is, this is actually what? This is actually the root locus of the characteristic equation. That is what we need. But it is enough to plot what? It is enough to know what? know the open loop transfer function. You don't need the characteristic equation to find out the stability, because when we draw the root locus of this 1 plus gs hs, we have seen that the root locus starts always from the open loop poles. Now if you have a knowledge about this, you can find out the root locus, and the procedure is a different procedure. I have already told you this is not the procedure. This I'm just giving you just to understand what a root locus is. Okay, that's the first point. And what about the termination root locus? So this corresponds to the value of k is equal to 0. So the starting point of a root locus always correspond to value at k is equal to 0. Look at this. At k is equal to 0, S1 and S2 starts from 0 and minus 4, which is nothing but which is the open loop poles. Now the root locus terminates at terminates so in these two examples, so it terminates, or the terminating point is k is equal to infinity, right? So so it terminates, right? The root locus terminates. The root locus starts from an open loop poles, and root locus terminates at a point k is equal to infinity. Okay, so for this is the conclusion. And in the next example we'll see a different example, and we'll understand something about more about the termination of a root locus. That is in the next session. Okay, hope the things are clear so far. Okay, so try to read this again, try to view this video again and again to understand the full concept of root locus, and we will see some more examples in the next video. Okay.